So guys, I guess we'll start. Just gonna share my screen and we'll go from there. So can you guys see my screen?
Yep.
Yeah, sounds good. So hi everyone, I hope you all are having a great reading week. Today's workshop is about an introductory session to blockchain. And hopefully by the end of this session, you will have a basic idea of what blockchain is and how it works. This is definitely not a deep dive because this technology is super advanced, and if you can actually, I think you might be able to get a degree on this, but we're just trying to understand the basics of how it works. So my name is Parsa, and I will be your host today, and I hope that you will learn something by the end of this session. So let's start by speaking about what even is blockchain. So I always like to look at it this way. Imagine that you have a I'm not sure if you guys had data structure courses, but always look at blockchain as just a simple data structure, which is just like a box where you can store data. But what makes it so special is that it's so difficult to change the data that is inside and stored in that box. And what makes it so difficult, we will get into the future slides, but it's just so fascinating to see that, imagine that you have a box and basically no one can actually change the things that are inside of that box. A few terminologies that we need to know is in blockchain, we have things called nodes, and these are represented by computers around the world. And each of those computers has a history of all of the blockchain, which we will hopefully speak about more. And whenever a transaction occurs, so this is a specific case of Bitcoin, for example, which uses blockchain technology. Whenever a transaction occurs, it gets validated by every single node, basically every single computer in that network, and then it's placed ahead in the whole blockchain chain in a way. And also, I would also like to note this, that blockchain is not only about Bitcoin. Bitcoin is just a digital cryptocurrency that is built based on the blockchain technology. And I would just like to give a very short history about how it actually came into the industry. So actually, blockchain was introduced by an anonymous person with a nickname called Satoshi Nakamoto in 2008, and he actually released this blue paper, it's like sort of like a blueprint, and it was just like among the hacker and sort of geek communities, and he was like, I made this cryptocurrency and it's built upon this technology, and it was actually very small in the beginning, and but I think Satoshi did a great job of, even though he was like basically unknown, anonymous, he actually reached to many different people in the world and he advertised his technology. And then what happened was, people like among the geek community started using this thing called Bitcoin. And in the beginning, it really didn't have much value. And like, as an example, someone actually bought a pizza. He like told the pizza delivery guy that I can pay you like 10,000 Bitcoins for just a single pizza. And, the guy agreed, and probably the whole pizza branch isn't worth that money at the moment, but who knew that this technology might be so successful? So let's look at some of the key components of the blockchain technology that play an important role of how blockchain works. So first thing is hashes. So what is a hash? I would like to first explain what's the hash function. So a hash function, you can just look at it as a function, just a regular function, that you give it an input, which has to be any size. You don't have any restrictions on the input size. And basically what that function should do is it should output a random string, which regardless of the input size, should be the same output length. And I will actually demonstrate that on this very nice website over here. So this is a hashing algorithm. It's called SHA-256, which is actually the algorithm used by Bitcoin. So imagine I just say like hi. So this is the hash for hi. And as you can see, this is like a specific length. And if I actually add just a single space, the whole thing completely changes. But as you can see, the length is the same, but the content is completely different. And it's basically impossible to go from the hash to the input other than actually brute forcing every single possibility and, checking if they're identical or not. And this is actually commonly used in like Facebook and different websites. For example, what they do is when Facebook wants to store your passwords, they basically store the hashes of your passwords. So they can, so if in any case the website gets hacked, the hackers can never actually get access to your account because your hashes are stored and they can't actually find your password. So let's say like my password was like 1234. This is what's actually stored on Facebook's data set. And what happens is like whenever I enter this on my user password profile, they check that they find the hash using just, the hashing algorithm. And then they check and see, oh, okay, so is this hash the same as the one that we've got stored? But the thing is, they can't go, like if someone hacks Facebook and they just have this, they basically can't find this value other than actually trying like going like 1 and then going 2, 3, 4 and checking every single value. And that's why they always say that you should use long passwords because, at some point it would just take like maybe centuries and millions of years to actually find the actual original password, which is pretty interesting. So yes, just going to continue with the slideshow. So that was the hash functions, but one thing that is very specific to cryptographic hash functions is the fact that they need to have 2 more characteristics. So they need to be very difficult to brute force. I mean, this is also common in like Facebook and other sort of reasons companies might use hashing functions, but they're especially important in terms of blockchain and using hashes in blockchain. Also, they need to be collision resistant. So what does this mean? Basically, if we have 2 inputs, they should never release the same hash output. So for example, if the hash of my password, which is like 1234, is this, there should be no other input that would release this exact same output. Meaning that like if I try all the inputs, like which would take years and centuries, I would never be able to find a hash other than 1234, which has the hash equal to this. Hopefully that was understandable. Do you guys have any questions? Oh, what other purpose does it have? So I think I might have caught your question a bit late. Is this regarding blockchain or hashes or? I'm assuming you mean blockchain because this was sent around like 607. So actually blockchain is used a lot in security these days. Many companies use blockchain to store some some companies use blockchain to store some information, and basically they don't want those information to be changed. And we will actually get into why blockchain is immutable, meaning that the data is stored and it can't be changed. But like, just imagine you're like a company and you have this box of data and you don't want anyone to be able to basically open this box, change its content, and then close it and, no one would notice. So this is one of like a very important use of blockchain other than cryptocurrencies. One more question, I'm just going to answer this one and we'll continue. So can you explain the brute force part again? Sure. So basically by saying brute force, it means that trying every single possibility. So imagine it should be difficult to brute force. So like imagine we have this hash function, right? It should be, so we said that the point of a hash function is we can never go from the output to the input. But by brute force, we can technically on paper find the input by trying every single input. Like imagine we have a super long for loop and then it goes like it tries all of the single possibilities and then checks if we ever reach the hash, so like 1, 2, 3, 4, if we ever reach this hash. And this is technically called brute force, meaning that we try every single possibility. And so when we say it should be difficult, we mean that, you know, it shouldn't be easy to just try all of the different possibilities and, you know, just find it by trying, basically. It should be difficult. It shouldn't be impossible because, you know, it's possible to make such a hash function, but it should be difficult. Hopefully that helped. So yeah, let's continue. So that was hashes. Now let's get to another important section of a blockchain network. So another important aspect is the mempool. I would suggest that you look at the mempool as, I'm not sure if you guys use, I'm pretty sure you guys use credit cards these days. So basically, you guys know when you like maybe pay something or you use your Visa card, and there's this like pending transaction section where it's actually not still taken from your account, but it's basically pending, meaning that like you go and buy like a PC maybe or something, and then basically you know, you buy it from Dell, you see on your credit card, oh, like $1,000 of pending transaction is on your account. It still hasn't actually been taken from your checking or Visa account, but it's just like a pending transaction, and you have to wait for it to actually be you know, approved and completed. So so Mempool is just, you can just look at it as a box, a database that stores all of these pending transactions which are still not confirmed and approved. And the next concept is a Merkle root. So this, oh, I actually forgot to change this part. I apologize. This is the same as over there, but a Merkle root. Imagine that you have a bunch of data and you want to find the hash of that whole data. An ideal, like an example that I do like to use in this situation is, imagine that you have your hand and every finger has its own hash. So like imagine like you have 5 fingers, every finger has its own hash, and you want to find the hash of your whole finger. And basically, so how would you do that? Do you guys have any suggestions? I mean, you guys can probably you guys probably have an idea maybe by looking at this image, but do you guys have an idea of how we can find the hash of like the whole hand if we have the hash of every single part of it? Or like if you have a room and then you want to find the hash of your whole room and you have the hash of all the different components of it. Like you have the hash of your desk, you have the hash of your bed. You guys have any idea on how we can do that? And by the way, guys, if you want to maybe like unmute yourself, it would be also pretty okay. So we can have this as interactive as we possibly can. So no ideas. So basically, that's totally fine. So basically what we can do is we can find the hash of every single component, and we can add those hashes together and then take the hash of that added hash. And then we can do this, and then like a tree structure, we can basically add the hashes and add all of the hashes together and then hash that, and then do the same thing, repeat the same thing. And then at the end, we end up with this root hash, which is the hash of the whole thing in one spot in a way. And you guys might wonder, why would we want to do that? Why would we want to have like one single hash for the whole blockchain, for the whole block, or for like our whole room, or for our whole hand? And the answer to that is quite simple. So we want to control the hashes, and we don't want to basically check all the hash of every single component. So basically, we can simplify everything by having only one hash representing the whole thing, if that makes sense. Do you guys have any questions on Mempool or the Merkle root? I know these concepts sound like a bit overwhelming. Hopefully, after I do like an actual conceptual demo of it, it would make much more sense. But if you guys have any questions, regarding this slide. So hopefully it was clear. Again, I think it will be much clearer when one question. So, seems to be good. That's great to hear. So that was the Merkle loop. So we have two more concepts, and hopefully after these two, we could actually, go and build something together. So what is a nonce? So nonce is just a random number that is generated, and it actually stands for number used once or number ones. So you guys can just look at it as a number, like a random number that you only use once. And then when you use it, you just don't use it anymore. So that was for nonce. It's actually a very simple concept, but it's very interesting, like the reason why we use nonce. And proof of work is a system so you can look at it as this. Imagine that you have a puzzle, which it has a specific difficulty level. And, you have like 5 people. In this case, they might be computers or just people. And they're trying to solve this specific puzzle, which has a specific difficulty level. And, you want to know like who finds the answer first. And the person who answers the puzzle first, they get a reward based on how difficult it was to solve that puzzle. So basically what happens is the person, in this case, who solves the puzzle gets a reward. And yeah, it's a very simple concept. But again, it's one of the building blocks of how the blockchain technology works. So now is the fun part. After all those, boring and plain explanations, hopefully we'll build something together. Do you guys have any questions on nonce or proof of work? Or you guys can also ask it like during the thing. Exactly, yes. Yeah. So we actually get into why and how we actually mine in Bitcoin. So I'm actually going to use Paint to explain how hopefully it works on a canvas, and then we can actually code everything together. So we said all these sort of stuff about blockchain, right? We said that we have these components to it. So how do these components all come together? So a blockchain is basically just, you can just look at it as some blocks that point to each other. And so this is the first block. It is, that is strange. So basically they are pointing to each other, and we have these blocks. And what happens, so the first block, we usually call this the genesis block. And basically, not much information is stored in this one, but it's just the first block in the blockchain. And when we have this first block, right? Every block has some information stored inside of it. So one thing, the first thing that is stored in a block is the hash of its previous block. So in this case, there's no hash in it. So I'm just going to make this small little section in each block that has the hash of the previous block. So this one's actually a null value because nothing's actually stored in there. So, this is completely nothingness here because, there's no data. And there's also a mempool inside. So basically meaning that there's this mempool where we have a list of all the pending transactions. So let's say, let's see, who do we have in our participants? Let's say we have Adam and we have Jessica. So basically, let's say Adam gives like 5 coins to Jessica. So Adam gives 5 coins to Adam gives like 5 coins, I guess. That might be a bit too much. 1 coin to Jessica. So these are like just some pending transactions that are going to happen. So this is the mempool, as we spoke about, and we also have something called the nonce, which is just a random number, as we spoke about. So I'm just going to put it here and different color. So there's also this nonce, which is over here. So the nonce, the actual transaction, and the hash of the previous block, as we discussed. And yes, I guess that's mostly it. So let's say, how do we find this block over here? So in this case, imagine we have like a few computers. In this case, these mining computers, and this is basically what mining is. So we have these computers, these 3 computers, and let's say one of them is Adam. Hope the text is not too small. Say one of them is Adam, one of them is Jessica, and one of them is, let's find another person from the audience. One of them is Stefan. So let's say, these 3 people right here, they're trying to mine the next block. And this is basically the terminology we use. They try to mine, they want to see who mines this block first. So what they do is, they, in their own computer, they make this imaginary block. They make this imaginary block in their own computer. And they have this imaginary block, which is like a template for this upcoming block that, they're trying to see who can mine this first. So what they do is they make this imaginary block for themselves. And inside of this block, they put the hash of the previous block. And the way they do that is they actually use the Merkle root. In order to find the hash of this whole piece, they use the hash of each of these individual components. And then they use that Merkle tree algorithm to basically find one single hash for the previous block. So, they find the hash of the previous block, which is very simple. This is not the difficult part, actually. We'll get into what is the difficult part, but so they put the hash of the previous block. They also put the mempool. It's not actually this mempool, it's the new transactions that are going to happen, basically. So like, let's say, Stefan gives Adam 2 coins. I should have used the same Stefan to Adam, but hopefully you guys get the point. This is going to be the mempool for this one. And we have the nonce again. So the nonce actually would be different for every single person. So until now, everyone did the same thing. They made a blueprint of the next block that they're trying to mine. They put the hash of the previous one over here, and they put, the pending transaction. But so one problem occurs here. So, basically, what they have, I'm just going to put the nonce, and things would make a bit more sense. So, we have the nonce over here. This would be the nonce. A nonce, as we said, is just a random number. So we can maybe start with 1. Maybe we can start with 1. So what happens is, let's say Adam is trying to mine this, and all these 3 people are trying to mine this single block over here. What they do is, I guess we do have the difficulty level as well. So what they do is they find the hash of this little piece of block over here, and they compare it to the difficulty level of the system. And what is the difficulty level, you guys might ask? It's just a number. It's just a number. So let's say the difficulty level is 1,000, for example. Let's say the difficulty level is 1,000, and what they do is they find the hash of this, each of these people. They find the hash of this, and they see if the hash is less than 1,000. And I mean, you guys did see, in the hash, we might have some numbers. We convert the hash into a number, and then we check if it's less than this difficulty level over here. And if it is less than that difficulty level, it means that we solve the hash basically, and we actually mined the coin. But this is rarely the case. So what is probably going to happen is, like, let's say Adam is trying to mine here. So he goes to this 1. I'm not sure if I can change this, but he goes and then he changes this to a 2. So basically comes here, and I'm not the best person with paint, but basically he finds the hash of this with 1, and let's say the hash is like 11,000. So it's like something like this. It's like, this is the hash. So let's say this is the hash. So the problem is the hash is actually greater than the difficulty level. So what Adam has to do is he basically has to go back and he has to change his nonce. It's this one over here. He can change it to 2. And then he finds the hash again. And as we said, the hash is completely random. So like a small little difference in this whole block would result in a completely different hash. So this time the hash might be like 3, 2, 1, 1, 2, 2. It might be, it's definitely going to be completely different from the previous hash. And basically what he has to do is he has to go to basically, he has to try all the different possible options for the nonce. He continues, goes to like 3, 4, 5, 6, 7 to infinity, and then he tries to find that specific value that when we take the hash of it, it's actually less than the difficulty level. So let's say he is super lucky, and he actually he goes with like maybe 7, and then when he tries 7, he's like, oh, the hash of this is actually like 9, 5, 1, 2, 4. Oh, and he's like, oh, I've mined this coin, mined this block. And what he does is, he announces this to the whole network, and he's like, oh, I mined this block. And basically what happens at this moment is this block is sent to every single other component of the block, so Jessica and Stefan, and they do have to verify that this is actually less than the difficulty level. Adam can't just say that this is less than the difficulty level until everyone actually verifies that. And one little important piece as well, and you guys might be like, why would Adam want to put resources of his computer to find this block? What's in for Adam? I mean, he is actually getting 2 coins from Stefan, but that's not the point here. Let's say, what would be the point for Jessica to block this, mine this block? So actually, there's one other important thing that I wanted to include after I explain this. So there's also one other thing, which is the reward. So the person who finds the hash that is less than the difficulty level would be rewarded with some amount of coins, which in this case, it might be Adam, Jessica, or Stefan. So basically, each of these people, so when Adam makes this blueprint, when he wants to mine this block, he puts Adam and then give Adam +2. So basically, he gives himself 2 coins in the reward section of the block, and he then starts changing the nonce. But Jessica does something different. Jessica puts the same thing, but he says Jessica +2. So this is actually very interesting. So imagine Jessica wants to cheat, or not Jessica, let's say like person X wants to cheat. And they actually hack Adam's computer, and they find the nonce that Adam found out. So they could use that nonce. So they would be the person who mines the block first, which sounds okay on paper. It should work, but the issue with that is on Adam's block it says Adam +2, so the reward goes to Adam. When this correct block goes to the network, these coins go to Adam. Whereas, if person X steals the nonce from Adam, it's not going to work for that person because this hash has Adam +2. And that's actually different from the, even though he found out the nonce, that's the nonce that works for Adam. And basically, if he wants to do that, he is actually going to, solve the, even if it gets accepted, the amount of rewards are still going to go to Adam's wallets, basically. And yeah, hopefully that's, a lot of information to take in. Do you guys have any questions on this? Yeah, hopefully that was clear. Yeah, so as I said, like this is definitely not everything about blockchain, but hopefully gives you just, a general understanding of how it works and, how you guys can just understand basically the concept. And this is actually what we call mining. The fact that each of these people have to use their computer to check all of these different possibilities to find this number that is less than the difficulty level. And basically, so I'm not sure if you guys, are in the news, how GPUs are becoming very low in stock these days, and they're very impossible to find because of people using them for mining. And the reason for that is actually like, why don't people use CPUs? So basically, they use GPUs because GPUs are very good at finding hashes and doing these numerical operations. And so, we actually some companies came in and they were like, why don't we try actually designing hardware, which is specifically like on the hardware level designed to solve just like hash, they don't do anything else because a GPU isn't just for solving hashes. It can do much more. It has all of these different sections to it that do much more. But some companies came in and they were like, why don't we actually design specific hardware just for mining, just for computing the hashes over and over again for millions and millions of tries? And this was the birth to some mining devices, like specific mining, which are like some examples are ant miners, which you guys can just search on Google, like ant miners. These are these devices that are just specifically for mining, and they're actually quite expensive, but they're very efficient because the only thing that they know is just computing hashes. And yeah, that's why they're super efficient in terms of just computing hashes, but they're still they still make a lot of heat and produce a lot of heat pollution. So let's go again through the concept of how blockchain works, and then we're going to go through the actual coding part, which is it's probably not as fun as the drawing, but you guys can actually try this on your own devices on Python as well. So let's see. First, a transaction is requested and authenticated. So imagine that we said, Adam wants to give 2 coins to Jessica. He sends the transaction to the mempool, and everyone has to actually check that to see like, if does Adam actually have 2 coins, or he actually doesn't even have any coins, which some conditions must be met, as we said. A block representing that transaction is created. So as we said, every single person in their mempool, they're going to have all of these information about these pending transactions. And then when the block is mined, the block would be sent to every other node. The person who mined the coin is going to scream in the network, oh, I found the block. And that's how it's actually going to be sent to every other computer on the node. And they validate the transaction as well. And then the person who mined the coin, who mined basically the blockchain, receives the reward, which is typically in cryptocurrency. So we said like, if Adam is the one who found the hash first, which contains the hash of the block, which is smaller than the difficulty level, he will be the one who receives the reward. And then when the person receives the reward, the block is then added to the blockchain, and it is the update is distributed across the network, and the transaction is then completed. One important thing that I think I forgot to tell you guys. So in the beginning, I did say that, blockchain, one important aspect of it is it's basically unchangeable, right? If we have some information, let's say, we have this hash over here. This actually gets accepted and it goes over here. This becomes the second block. So this is the first block. This would be the second block. And let's say we go, we go for a while, and this blockchain actually grows, and we have like maybe 100 blocks on it. So, we continue, we bring more people, Adam, Jessica, Stefan, we bring a few other participants, Takvir, Sina, And what happens is, we get a lot of popularity in our blockchain, and we might have like 100th blockchain over here. So what would stop, what would happen if, let's say, person X, is that hacker that we had, who was trying to use Adam's nonce, he actually tries to go back, and he actually tries to alter this, like maybe alter the second block. And he goes and he tries to change, like, Stefan gave Adam 2 coins. He tries to say like, oh, Stefan didn't give Adam 2 coins. He gave Mr. X 2 coins. So he goes like, oh no, this is not correct. Stefan gave me, Mr. X, 2 coins. Do you guys see what might cause a problem here? Why would he not be able to do this? You guys have any ideas on this? What would happen if, he changes Adam's wallet number to his own? Exactly. So basically, because the next block, which is block number 3, would have, so let's say this is block number 3. I didn't include it over here, but let's say block number 3. It actually stores the hash of this block number 2, inside of it. So if Mr. X changes the receiver, the hash of the whole block will change. Like, even if we add like a space between Adam's name, in this case, in Bitcoin, it's actually Adam's wallet number. But if we just add a space in his name, it's going to completely change the hash. So let alone, just changing the name altogether. And this makes blockchain so powerful. Basically, if one little piece of the block changes, like one single section of the block, the whole blockchain would be, would fall apart. And that's what we also said over here. When we said nodes validate the transaction, and the transaction is requested and then authenticated. Another part of being authenticated is that they actually go and then they check, oh, are the hashes correct? Do things make sense? It's not like when the person is mining this one, they can change the hash of this one, because all of the other blocks would actually be able to authenticate this. And actually, this brings us to a very interesting topic. How would you guys think like blockchain could be vulnerable? Do you guys have any idea? I did like give a hint. So look at it like this. Imagine if someone, like, we said that each of these people have the power to authenticate the blockchain. What do you guys think might cause a problem? Let's say Adam, he's super smart. Let's not say Adam. Let's say, Adam is smart, but let's say Mr. X, right? This bad guy. He actually comes and then he buys like 10 computers. And, probably not going to have space for 10, but let's say he buys 4 computers. He actually has more voting power than these 3 actual people. And what he actually can do is he can like do something in the block. And then because he has so much influence, he can actually, change change transactions. And, even if they were like to vote and to verify something, these are more than he has 4 people power compared to 3 of actual people. And if all of these 3 people, like even if all of them vote for the truth, Mr. X has, more computing power. And that's why he actually gets control over what would go with the blockchain. And this would actually break the whole blockchain, because, there's going to be no more trust in it, and no one's going to continue using it. So this is actually why, if you look at the Bitcoin mining pool, you can see that none of the pools have actually more than 50% control. So I think the maximum is like 34 or something. And this is like the highest highest computing power in terms of the whole like a fraction of the whole people using it have. So that's why it's actually called the 51% attack, which kind of makes sense. If one person gets a hold of more than 50% of the the power of the blockchain, they actually are super dangerous, because they can do whatever they want with the chain. And Yeah, hopefully that makes sense. Yeah, I just thought that might be an interesting topic to share with you guys. So do you guys have any questions on, how it works and just, the things that we explained over here? If not, we can go to the coding part. So hopefully it was clear. And let's go to the coding part. So I actually use WSL, but it should be pretty straightforward for you guys. Just opening a Python file. I'm just going to open a Python file. Let's just call it GDSC blockchain. So I'm just going to go there. And I'm going to make a Python file. You guys don't need to worry about these parts. These are I'm just opening Visual Studio Code. Let's call it blockchain.py. Yeah, and Gordon also posted the link of the code you're using here. And so basically what I did was I opened like a IDE, in this case, Visual Studio Code. And yeah, let's actually start with the code. So I'm actually going to basically use the one that is posted because you guys can actually follow along and actually understand how it works. So we're going to be using two libraries in our code. One would be date time, and one would be hashlib, which we use because it's basically a built-in library in Python, which you guys all should have if you have Python installed. And what this does is basically you can use it to take the hash of anything, which is pretty nice and it's pretty handy in our case. Then we're going to define a class, and if you guys don't know what a class is, we're basically just making a specific object, like yes, you will have access to the recording afterwards. What a class is, it's basically you can make objects with specific identities that you need. So you actually don't have to understand classes for the sake of this, for the sake of learning how blockchain works. But we're just going to use classes because they're so powerful. But again, it's very straightforward. Hopefully you guys will understand. We're going to define a class called block, which is basically just a block object. And it's going to have specific identities that a block would have. So what do you guys think a block should have? The first thing would be a block number. It's basically like, as we said over here, every block, we have like block number 1, block number 2, number 3, all the way to 100. So each block is going to have a number. For now, we're just going to set it to 0, just because we haven't actually made any objects yet. And then we're going to have the data, which is the data stored inside of that block, which this consists of the mempool and all of the pending transactions. So for now, it's going to be none because nothing is stored. We haven't added any transactions yet. And we're going to have the next block, which we also spoke about. We are also going to have the hash of that block. I'm not sure why this is colored yellow, but hopefully that won't be an issue. So we have the next in the hash of the current block. We also have the nonce, as we spoke about. And we just said, so as you guys can see, 0, none, 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 0. So these are just like a template of how we're going to define a block. So we're going to have the nonce set to 0. We're also going to have the hash of the previous block, which I'm going to call previous hash. And I'm going to set it equal to, so I know this might sound strange, 0x0. What this means, this is just like a hexadecimal number. This is just like for formatting stuff, but it basically is like a null previous hash. Hopefully that's clear, but it's just like a way to represent a hexadecimal none value. Then we're going to have a timestamp, which, it's just nice that it's not necessarily for this blockchain, but, it's something that is used on Bitcoin. And if we're going to have an actual network, we actually really need to have a timestamp because we need to validate the time and, the date which each transaction has occurred. So we're going to have a timestamp, and we're going to set it equal to date time dot date time now. And this is basically, the current date and time. Very simple, hopefully. Then we're going to have a init function. Whenever we define a class, the init function is basically a function that gets called whenever we define a object from that class. So basically, whenever I make a block, this function is going to run. Just that, basically. So we're going to have def init and a self. This self is always there, like whenever you want to define a class, in the init function, you're always going to have the self. This is going to be probably pretty useful if you guys are going to take any object-oriented courses regarding Python in the future. And we're also going to have the data here. And we're just going to assign self.data is equal to data. What we're just saying is this data over here is going to be self.data of that block. I mean, we can also say like self.something else, but just to make things simple, we're just going to use self.data is equal to the actual data. And so whenever we actually define a block object, this function would run. We're also going to have one other function. We're going to call it hash. And what this is going to do is it's going to basically return the hash of that block, basically, as we said. So the only thing that we're going to put here is self. We're not going to use any of those previous ones. And what we're actually going to do is, I know this might sound very like unintuitive, but we're actually going to, so now we're going to use the import hashlib library to basically take the hash of this whole block. And just to make things simple, I'm just going to point out that we're not going to use Merkle root tree in this specific code because that would be a bit too complex. So I'll tell you guys what we're going to use instead of that. So we're going to just say h is equal to hashlib dot SHA-256. And these are just like, if you actually go to like hashlib over here and, you find like tutorials on this, to use it, you have to use like this specific, like they usually use like h equals hashlib. And we're going to say h dot update. And what we're going to do here is, so you guys remember we said, if you want to find the hash of the whole thing, we like add the hash of each of the individual components in the Merkle root section. So now what we're going to do is, just to make things as simple as we possibly can, we're actually going to add all of them, not like adding 2 by 2 and then hashing. We're just going to add all of them directly, which, it might not be as secure and as professional as a Merkle root tree, but it works in our specific case. So we're going to say string str. This is a casting, and we're going to say self.nonce. So we're just going to have the hash of the nonce. So we first convert the nonce to a string, and then we encode it. And we're going to also include UTF-8. And this is just a coding format, which you guys don't really have to worry about for now. And then we're just going to, so this is going to give us the hash of the nonce. We're just going to add the hash with, again, str. And this time the self.data. So this would be the hash of the data, encode, and UTF-8. And, we're just going to keep on adding these. So we had the nonce, the data. We need to have the previous hash. So again, str self.previous hash. And we would put encode and UTF. Oh, got the quotes. UTF-8. And, we're going to continue for all of these parts. Hopefully it won't end up like a super long line, but then we're also going to have str of the, so we had the previous hash, now we're going to have the timestamp. So self.timestamp, timestamp, and we're going to encode this again, UT-8, and just just to make things a bit faster, I'm just going to copy this and change that specific part that actually changes to be a bit more efficient. So for the next one, it's not going to be the timestamp, it's going to be the block number. So block number. And that's basically it. We just add all these together. And I'm just going to put the parentheses here, and we basically find the hash of that whole thing, like the whole added hashes. And that would be the hash, and we just return h.hexa digest. And this is basically just the hash. I'm not going to make it super complicated, but it's just going to be hex digest. And so that was that. And we're also going, I'm just going to do one more thing. There's, I'm not sure if you guys are familiar with classes, but there's also this they call these magic functions, like this init one. And there's also another magic function, which is called str. And what basically this one does is whenever we print that object, we can say that, rather than printing the memory, we can say that print a specific thing. So in this case, we're actually going to print, some information about that block just to, so when we actually are finished with the program, we can gain some useful information from it. So what we're going to do is we're going to return. So what do we want when we want to print a block? So some things that might be pretty useful is the hash of that block, just to see, it works. So the hash of that block is something plus, and then str self is just the hash of that block, basically, hash. And this is the hash that we get from the hash function over here. We also can print the block number. We can have, and you guys probably know, we have string concatenation. We can add strings together. So we can also say on the next line, we can put a new line, and then we can say block number. And then we can put the block number. So plus, I'm just gonna copy this. We can make it a bit faster. And then we can put block number. And then what else might be useful? We can put also the data inside of it and the number of hashes it took to actually find the hash which is less than the difficulty level. So let's also put the block data, a new line, of course. So the block data, and this would be self.data. And also we want to add the number of hashes it took for the block to solve and basically mine. So we can also put another new line and say hashes, and this is plus, and self, this would be self.nonce, because the thing is, The self.nonce, what it does, it returns the nonce. And the way that we're actually going to approach the nonce is we're just going to increment nonce by 1, just to make things simple. And basically, the number of hashes that we check is going to be self.nonce because we're just incrementing the nonce by 1. So it's going to be self.nonce. And that's it for the block function. You guys have any questions regarding the block function, like why we added something you guys didn't probably understand, or you didn't need this? Is there any specific things you guys found a bit confusing, or I need? Sorry. Sorry about that. Self. Oh shoot, these are all. Yeah, thanks, Stefan. I am not sure why I said left, but yeah, thanks for that. That's up. So yeah. So then let's go to the actual blockchain class. So class, and this time blockchain. And some like useful thing you guys might find useful is when we define classes, we usually use capitals at the beginning of that class name. This is actually not super important in Python, but I think it's very like you have to have this for C++ or Java. They just have a nicer code. It's like a kind of standard that they use. So class blockchain, and what do we have here? So we're going to have a difficulty level of the blockchain, and for now we can set it equal to 20. And we also have a max nonce, which is basically the maximum number of nonces that we want to try. We're not going to burn our computer and run a forever while loop. We're actually going to have a maximum, which is going to be 2 to the exponent of 32 in this case. And we're also going to have a target, which is based. So I'm actually going to write this and then I'll explain it. So it's going to be 2 to the exponent of 256 minus the difficulty level. So let's say the difficulty level is 20. The target would be 2 to the exponent of 236. But let's say the difficulty level is much higher. So it's like 100 difficulty level, right? That would mean that this number would be smaller, right? So basically the thing that we find, the nonce that we find, and then the hash of the block should be less than the target, which is, the lower the target is, the lower our probability of finding it will be. So the higher the difficulty level, the smaller this number would be, meaning that this whole number would be smaller, the target would be smaller. And what happens then is it means that we're going to have a more difficult time finding that specific hash that solves the problem for us and helps us to mine the coin, or it doesn't have to always be a coin. And we're also going to make a block. So every single blockchain would have a genesis block. So we're going to say the first block would be, the genesis block would be a block, and then we can call it genesis. And then the next line of code might be a little bit strange for you guys. I'll try to explain my best why we do this. So we're going to say dummy equals head equals block. And the reason, you guys might be like, why do we even have this dummy? Why can't we just say head is equal to block? And basically the head is the latest block, the most front block in the chain. And why do we actually use this dummy is just because of Python in this case. So the way that Python works is it actually assigns specific memory, it allocates memory to objects, meaning that if we just say head equals block, if we change the block, it will change the head. And basically we are not going to have different memory spaces for each of these. So like a nice way around this issue is to use dummy equals head equals block. And this way we're actually putting different space for head and a different space for the block. Hopefully that was clear for you guys. And then, so these are like the basis of our blockchain function. Then we're going, and guys, quite near the, like close to the end of the code. So hopefully we'll manage to finish this. I know it's past an hour, but then we're going to have a add, which basically what this add function does is it adds a new block to the end of the chain. So we're going to have self and a block. And what this does is we're going to do block dot previous hash would be equal to self dot block dot hash. So basically what we're doing here is we're going to assign the previous the hash of the previous block. The value that we're going to assign to that is the hash of the current block, and then we're going to move the head block one step ahead. Do you guys understand what I just said? So what we're going to do is we're going to put the hash of the block in the block.previous hash, and then we're going to move the head of the block one step forward. And then that would make sense, because then the hash of the previous block would be the hash of the previous block, because the current block would be the one in the front, basically. And we're going to have block number, sorry, block number, block number, and this would actually be self block number, and then +1. As we said, this is the one in the front, so we're adding one block to the front. And so that was just the add function. And the last function that we're going to have is going to be a mine function. We're just, if we have a blockchain and we can't mine it, then what would be the point? For the mine function, we're going to have a self, as always, and a block. We need to know which block we're mining. We can't just randomly mine anything, like something. So we're going to define the mine function, and we're going to say for n in range, and then we're going to check all of the different possibilities up to the max nonce. So max nonce, and we're going to check all of the different possibilities, and we're going to say if the integer, because it's actually a string, the hash is a string, we convert that block dot hash into a integer, and then we actually convert it into a 16. So this 16 over here is basically converting into a 16, the basis of 16 integer, basically, for the integer function. And then we're going to say, as long as this is less than the target, so if this is less than the target, self.target, that specific difficulty level that we came up with up there. So we said that the target would be over here. So when we reach a point where this is equal or less than the target, what we're going to do is we're going to add that block to the chain, because we basically mined it. So self.add, then we just add that block. And I guess just to be fun, we can just write like print, yay, we mined the block. And the next thing, so if this is the case, we mine the block, but this is going to be rarely the case. And what's going to end up happening 99% of the times is we're not going to get, something that is less than the difficulty level. So we're just going to increase the nonce, which is, that just random number that we had. So plus equals 1. And that's why we said that. So if you guys look at here, we said the number of hashes that took is actually the number of the nonces that we checked. So if we continue and if we go run the mine function, and then we see that this works with a nonce equals to 1,000, that means that we used 1,000 different nonces, meaning that we tried 1,000 different hashes, and then we can we get a sense of how many hashes we tried. So that's why we use hashes. That would be the nonce value. And so that was that. And so if that's not the case, we just increment the nonce by 1. So let's actually just test it out and see if it works. So we create an instance of the blockchain. So we're just going to call it, let's call it GDSC blockchain. GDSC blockchain. Sorry, it should be a capital. So blockchain. And so right now sorry, I have to say GDSC. I'm going to copy this. So GDSC blockchain. So the GDSC blockchain is equal to a blockchain, a class. We're just making a variable which its identity is a blockchain. It's similar to when you define a variable and then you say that this variable is a string type or an int type. We're saying that this GDSC blockchain is a blockchain type. And what we're saying is for I in range, let's say we're trying to mine like 10 blocks. So we say for I in range 10, what we do is we mine the block. So blockchain, in this case, it's actually GDSC blockchain. It's not any blockchain, it's our blockchain, our group's blockchain. So GDSC blockchain dot mine, and then we do block, and then we say, we're just typing this because we want to know which, like when we print it out, you guys will see. It just makes things a bit nicer. So we say block, and then plus string. So basically, it's going to type down the number of the block that has been mined in this case. So we're just going to type in n plus 1, and n would be the thing that we set here. So now we're going to the mine function, and then when we say n, we're just trying to print n plus 1, saying that n starts from 0. So we're just writing that, oh, the first block is this, the second block is that, the third block is that. This is just a way to write that down. And then so that was our for loop. We're going to mine it that many times, and then while blockchain. In this case, that would be the GDSC blockchain. I added this in the end because I thought, why not? So the GDSC blockchain, the head of the blockchain would be none. So, we don't want to have a empty blockchain. And basically, a blockchain has to have a single genesis block. So we're going to say dot head is equal to none. Is not equal to none. And we are going to say print the GDS blockchain dot head. And we're also going to say blockchain, GDSC blockchain, GDSC blockchain dot head is equal to GDSC, and I'll explain this code just in a second. Dot head dot next. So basically what we're saying is then the head would be when we go to the next block, we're basically assigning the head of the original head to the next block, because the head gets updated in it every time we mine it. So we're just saying that the current head would be the head of the next one, which would be the current one. Hope that makes sense, guys. And let's actually run this and see if it works and how it works. Hopefully you won't get an error in our first try. So it's going to be Python 3 blockchain.py. Oh, sorry guys, forgot a parentheses. So line 21. This extra? Yes, it's probably extra. Line 25. Oh, I forgot the, sorry. Line 25. So So the hashes str. That is odd. Just for the sake of time, I might go to the code that I sent. And I'm just going to copy line 25 from there, so you guys can actually see how it works. Line 25. I think it was this one. 25. The string. So def. Just going to copy this and use this one. Yeah. And let's try that again. I've got line 51. So, you know, when you run a code, it rarely runs on the first try, especially when it's a bit long. So run line 51. And again, probably just going to copy from the other one. So it's GD. So we said I might as well just copy this whole chunk just to make sure that nothing else arises. Yeah. Fortunately, we had to give up on our GDSP. Oh, I said Nonce. Sorry for the typing here. So max. So max Nonce. Hopefully it will work this time. Seems to be a good thing. Oh. Guys, and actually what I'm going to do is I'm going to copy this whole code. The code is correct, like the one that I wrote, hopefully, but there seems to be some, I think there's probably some mistakes in the syntax, but just so you guys can see how it should properly work. So basically what should happen is when you run the code, as you can see, it actually starts mining 10 times. And yes, so basically you can see the block hash. This is the hash of that specific block number, the block data, and then the number of hashes that it took. So if you guys can see, it actually took around 3 million, more than 3 million hashes to find, like basically mine this one. And you know, these ones, it took 11 million. So yeah, it's actually much more in terms of actual Bitcoin, but yeah, hope you guys found this interesting. And yeah, thank you so much. I apologize for the inconvenience that happened at the end of the presentation. It was a bit difficult to, I'm actually not using my main monitor and I'm using a small laptop, so I wasn't able to see very clearly the text. And yeah, some small syntax errors came up and I apologize for that. Do you guys have any questions regarding the presentation? Like, or regarding anything blockchain? Thank you so much, everyone. I hope you guys found this information useful and interesting. And I wish you guys a happy reading week.